Hello everyone, I am Bharat Singla and welcome to Learn Competitive Programming with CodeChef. If you desperately want to master competitive programming and get your hands dirty in data structures and algorithms, then this is a one-stop destination for you. Every week, we upload problem explanation from CodeChef's contests, conceptual videos on various programming paradigms, and also conduct live interactive sessions. But before we start off, here's a reminder for you to hit the subscribe button if you haven't yet already. Great. Now that you have subscribed, let's get started. So today we'll discuss the problem Sed Password from CodeChef December Cook Off. If you are very familiar with the concept of bit masking, then the problem should be easy. But in general, I think the difficulty level is medium hard. So let's get started. So let us quickly jump into the problem statement. So given a string S that will only contain lowercase English alphabets from A to Z and question marks, right? We need to find the number of good substrings in S. Fine. So like S, this is one valid S, yeah, because it only contains lowercase letters from A to Z as well as question marks. So this is one valid S. Now a substring R, let's say R of S is good if the parity of each letter from A to Z matches in S and R. That is, each letter from A to Z should either occur even number of times in both S and R or odd number of times in both S and R. Fine. So like if I take the substring AB, is this substring a good substring? For that, what we can do is like the letter A is occurring odd number of times in this substring, only one times, and in S it is occurring even number of times, two times. So AB is not a good substring. Fine. So since the parity of each letter does not match, and it is also given that if R contains any question mark, then all the question marks in R must be replaced, and that too by the same letter. So now let's say if I take the substring from first index to the third, that is AB question mark. So this is the substring AB question mark, and I can replace the question marks with any letter. But now notice that if I replace it with, let's say A again, so I end up with the substring ABA, and now note that ABA's parity exactly matches with the parity of S, because A is occurring even number of times and in S also it's occurring even number of times. B is occurring one time, that is odd, and in S also it is occurring odd number of times. Fine. And here in S we are not considering the frequency of the question mark. Fine. And for C, D that are not occurring in both of them, they are occurring zero number of times. So if a character is not occurring, the parity is still same because zero is also even. Fine. So AB question mark is a good substring because it can be optimally replaced by A, and then the parity matches. Fine. So this is one good substring, and out of all the possible substrings, we need to find the number of good substrings of S. So now that we are comfortable with the problem, let us move on to the approach. And this will not just be the solution, it will also include the intuitions and how you can approach these kinds of questions. So firstly, one very important observation, one key point to note is that no matter how long S is, like what's the length of S, it's only going to contain at max 26 or more precisely 27 characters. Fine, because there are only 26 alphabets. Yeah, so now the problem suddenly starts to look much simpler, and we are going to leverage this fact throughout the course of the explanation. Fine, so let me just quickly first define a bit mask. So a bit mask, the type of bit mask that I'm using here will be around 26 or 27 bits long, where the ith bit will denote the parity of the ith alphabet. Fine, and 0 if the ith alphabet frequency is even, and 1 if it is odd. So to make things clearer, let me just take an example of S, the same that we took above, that is A, B, question mark and A. Fine. So how will the bit mask of this S look like? So mask of S, and let me just denote it by MS. So mask of S will be 26 bits long, considering that we are not taking care of the question mark. And the first bit will denote for A, the second bit will denote for B, the third bit for C, and so on till the 26th bit for Z. Fine. So A is, since A is occurring even number of times, so it will have 0. Then B is occurring odd number of times, so 1. Then C is even, so 0 again. D is also even. Fine. And so on till Z is also even, so 0. Fine. So this will be 26 bits long. Fine. So this is the bit mask that I'm using, and this will help us to quickly identify if a letter is occurring or a character is occurring even or odd number of times. Yeah, because taking the frequency mod 2 and then checking if it is 1 or 0, I have simply defined this bit mask, and here if I want to check if A is occurring even number of times or odd number of times, I don't need to do that mod 2 stuff. I simply can see for 0 and 1. Now let us make an observation that for a substring to be good, its mask should be similar to that of the mask of S. Only then can I say that the parities will match. Yeah, so this is one good observation, that for a substring to be good, its mass should be similar to that of S. Fine. So now what is the criteria for a substring to be good? Fine. So there are two cases mainly. That is case number one. This stands for even number of question marks. Fine. What if my string that I am taking contains even number of question marks? In that case, for my string to be good, for my substring to be good, the what should be the mask of that substring look like? So here the mask of the substring should be exactly same as the mask of S. Now why? Because note that the question mark, no matter which character I replace it with, it's not going to change its parity. Like if I replace the question marks with A, and if A was before replacing occurring even number of times, then even plus even is even. So after replacing also it's going to occur even number of times. So 0 in the mask will say 0. And if it was occurring odd number of times, then odd plus even is odd. So again its parity has not changed. So no matter which character or which letter I replace the question marks with, it's not going to change its parity. So for a substring with even number of question marks to be good, its mask should look exactly same as that of the mask of the input string S. And remember this plus 0. Fine. Now this is a 27 bits long bit mask for the substring, and 0 basically denotes for question mark. And since we are taking the case for even number of question marks, so that's why 0 for the question marks parity. Fine. So this was the first case, and now the second case with odd number of question marks. Fine. So if a substring has odd number of question marks, then what should its mask look like? Fine. So now notice that if I replace let's say I replace all the question marks with A, so it's going to change the parity of A. Like no matter which character I replace it with, it's going to toggle its parity. Like if it was originally occurring even number of times, then now it's going to occur odd number of times. And if it was occurring odd number of times, then odd plus odd is even. So now it's going to occur even number of times. Right? So the character by which I replace the question marks with, it's going to toggle its parity. So now for the mask, so the mask of substring should be similar to that of S. The only thing is that one of the bits should be mismatched. Now why? Because the question mark is going to compensate for it, right? If let's say if the parity of A does not match, then I can replace the question marks with A, and now it's going to match. Fine, and so on and so forth for the 26 alphabets. Fine, so I can replace the question mark with that letter whose parity I want to be changed. Fine, so initially in the mask of the substring there should be one bit that should be mismatched. So it should be the mask of S with, let's say, the first bit toggled. Fine, so the first bit toggled, or the mask of S with the second bit toggled. Fine, so until the mask of S with the 26-bit toggle. Right? In all of the cases, if the mask of my substring looks like any of these 26 masks, then I can say that my substring with odd number of question marks is good. And this, remember, with plus 1, because here we are taking the case of odd number of question marks. So this is again a 27 bits long bit mask. Fine. So now we have ended up with total 27 possibilities. Yeah, the first one was for even number of question marks and 26 for odd number of question marks. So what we can conclude is that if the mask of my substring looks like any of these 27, then I can say that my substring is good. Right? So 27 possibilities. So now let us try to apply this the same that we have learned here. Now one thing to notice is that the constraints are very high. Like the length of the string could be as large as 10 to the power 5. So here it's not even possible to form all the substrings. So in this case, I highly recommend that you just try to work with prefixes. Fine. So the next observation that we are going to make is that any substring can be represented as a smaller prefix subtracted from a larger prefix. So like if this is the string that you have, fine. So how can I represent this part of the string? Like how do I represent this substring? So I can represent it as the prefix that like the prefix always starts from the first character, so until this position minus the prefix starting
from the first till this position. So if I subtract this prefix from this prefix, I'm going to get this substring. Fine. Exactly same as you do in the prefix sum technique as well. You subtract the sum of this part from this part to get the sum of all the elements from this part. Fine. So we can apply something similar here as well. So can I say that to get the mask of the substring from, let's say, j to I, from j to I, can I say that this is nothing but the prefix mask? So prefix mask till I minus the prefix mask till j. Fine. Like if this was I and this was j. Fine. So I can simply, or this was j. So I can simply subtract the prefix till I minus the prefix till j. So I can get from j to I. Fine. And just bear me about not taking j plus 1 to I. Fine. That is something more precise. But this is how you can represent any mask. But notice that here the masks are not something that is subtractable. Right. Like in prefix sum, you can subtract two sums. Fine. But here, these masks do not denote something like the sum or the count that is subtractable. They instead denote even and odd. So instead of minus, how should I combine these two prefixes? Now this is the main question. Now notice that again, let me just redraw this string. So this was the string that you have. Fine. And let's say if this is J and this is I. So how do you say that how can we basically get the frequency of the letter, let's say A, from J to I? So in this substring, how do I get the frequency, the parity of the frequency of A? Well, if I know till J, so if till J, let's say it is even number of times, and till I, it is, let's say, even number of times again. So can I say that 0 and 0, that is for I and J, 0 and 0 should give me 0 again, because this means that from j to I also the frequency should be even. Only then even plus even is going to give me even. Fine. So 0 and 0 should give me 0. Fine. But now let's say instead of this 0 I was given 1. So what should 0 and so what should 1 and 0 return? Fine. Well, it should return 1. Why? Because even plus odd will give us odd. Fine. So here I can say that the parity of frequency is odd. Now let's say here I was given 0 and here I was given 1. So till j it's occurring odd number of times, till I it is even. Well, again I can say that this is nothing but 1. Yeah, odd plus odd will give me even, and for 0 and 0 as well. Sorry, and for 1 and 1 as well, we can clearly observe that it is 0, because only can I say that odd plus even will give me odd. Fine. So 1 and 1 is also 0. Now here comes the beauty of the question. Notice that this part, these like 0 0 is giving 0, 1 0 is giving 1, 0 1 is giving 1, 1 1 is giving 0. This is nothing but the XOR operator. Yeah, the XOR operator. Fine. So can I say that prefix mask of I XORed with prefix mask of j will give me the mask for the substring from j to I? Yes, I can. So here instead of minus, I can replace it with XOR. So now for a substring to be good, it should match with at least one of the 27 masks that we discussed above for a good substring. So can I say that prefix mask of I XORed with prefix mask of j, if gives us any good mask, then the substring from j to I is good? Yes, I can. So now one important observation is that notice the LHS is still n square, right? For every I, we need to check all the previously encountered prefixes. So this is n square, right? The LHS is still n square. So how do we reduce it further? Now there's one property of XOR that if A XOR B is C, then A XOR C is B. Fine. This is a property of XOR. You can try it for different number as well. So now can I rephrase this? So can I write that the prefix mask of I XORed with any good? Fine. So if this XORed with any good is giving me any prefix of j, any prefix mask till j, then again can I say that j to I is good? Yes, I can, because I've not done anything that is too complicated, and I've simply taken this part to be here and this part to be here. Fine. So I just use the property of XOR. Now notice that there can be at max 27 possibilities, and this is O of n. So the LHS I have reduced to O of n now. Now just as a side note, I want to convey this that now this I know that bit masking can be a little complicated topic for a lot of you, and new topic as well. So I highly recommend that you just rewatch the video twice or thrice so that the concept really sticks in your head. Like this is a very beautiful problem of bit masking and a really good application. So if you get the confidence and you get the approach of how to solve this question, then maybe you can solve any bit masking question as well. So this is a very important question, and that's why I recommend that you watch this twice or thrice or till the time it sticks in your head, right? And you start to feel very confident that yes, I can now solve any bit masking problem. Fine. So just as a side note. Now notice that we have brought it to often, but this still is often. So what I can do is instead of storing all the prefixes in a list, what I can do is I can store them in a dictionary or a map so that I can reduce this part too often as well. Like we only need to check if there's any prefix mask J which matches with the LHS. Yeah, for that, why do we need to traverse in the array? Why can't we simply maintain a dictionary where the key is the prefix mask, and the value is the number of times we have seen that. And now we all know that in dictionary or a map, the retrieving of a value is very fast as compared to a list or an array. Fine. So now instead of storing all the prefixes in a list, I can store it in a map. So let's take an example that, let's say, prefix mask of 4 when XORed with, let's say, the first good mask that was for even, if you remember. So G1, let's say, gives us a mask that matches with the prefix mask till 2 and prefix mask 3. Both of them match with this. So can I say that in the first case, the substring from 2 to 4 is good and the substring from 3 to 4 is also good? Now why? Because this is nothing but rephrasing the equation. So if I bring PM2 here, so I basically mean that PM4 XORed with PM2, that is nothing but the mask of the substring from 2 to 4, it matches with any good substring. Fine. So from 2 to 4 it's good, and same goes for 3 as well. From 3 to 4 it's also good. So can I say that if PM4, let's say XORed with G1, is giving me the mask I've seen 2 times earlier, so, and it does not matter for which 2 times, since we don't need to tell the substring, we only need to tell the count of the number of good substrings. So can I say that once I found this mask, I can search in the map how many times have I seen this before? If I have, let's say, seen it 2 times, this means that there must be 2 prefixes that I've encountered earlier, and that when XORed with this will give me a good substring. Fine. So here, like, this mask matches the count. The count of this mask in our map is 2. So can I say that I can simply increment my answer that I'll print in the end by 2? Fine. So this is the approach. This is the broadly the approach. And notice that the time complexity is O of n into 27. Fine. 27 possible good substrings. Then for every I we are going to check. So O of 27n, that is O of n. And here, since we are maintaining a map and only incrementing our answer by the value that the this XOR is giving us, so this the RHS is also O of 1. So the complexity turns out to be O of n. Fine. So this was the approach. Now let us just quickly summarize what we have done. So first, we just quickly fetched the mask of S, where the ith bit denotes the parity of the ith alphabet. Then, for a substring to be good, there were 2 cases. The first case, where our substring contains even number of question marks. In that case, the mask of the substring should exactly match with that of S, because question mark, no matter which character it is replaced with, it's not going to change its parity. And that plus 0 denoting that there are even number of question marks. So 27 bits long bit mask. Then case 2 was when we have odd number of question marks. So in that case, the mask should be similar, but notice that since the character that the question marks are replaced with, it's going to change its parity. So initially there should be one of the bits that are toggled, fine, so that the question marks when replaced matches. Fine. So initially there should be something mismatched so that after replacing it matches. So either the first bit could be toggled. This means that I can replace it with A. So after that, it changes the parity and now it matches, or the second bit toggled, or the third bit toggled, so until 26th bit toggled. And that plus 1 denoting odd number of question marks. So in total, there are 27 possibilities for the mask of a substring to be good. Fine. Then we saw that to represent any substring, what we can do is we can simply subtract 2 prefixes. Fine, like we do in prefix sum technique, but here we cannot simply subtract them. So here we saw that instead of the minus operator, we can do the XOR operator. So the mask of substring from J to I is nothing but the prefix mask till I XORed with prefix mask of J. Fine. Then we saw that now this is a general mask of a substring, and this, for it to be good, this should match with any good mask. Fine, out of the 27 possibilities that we saw earlier. Now what we saw that here we are ending up with still an O of n square algorithm. So how can we optimize this? Well, we used the property of XOR, that was if A XOR B is C, then A XOR C is B. Fine. And so PMI XOR with any good mask, if it is giving me any prefix mask that I've seen earlier, that is any PMJ, Well, in that case, the substring from J to I is good. Fine. And now here we have reduced the LHS to O of n and the right also till O of n. Fine. But now what we saw was here to match with any prefix that I have encountered earlier, instead of using an array, I can use a map where the key will be the mask and the count will be how many times have I seen that mask. Fine. So the key will be the mask and the value will be the count of how many times I have seen it earlier. So now we have reduced this to O of 1 or O of log n like very fast. So this is nothing but O of n now. And one thing to notice as well that we missed here was that like if this is the string or the array, so I can represent the mask of j to I as the subtraction of two prefixes. But what if we are given the substring from the start only? So like if this is the substring and like if this is the string and I want the substring from this to this, right? So in this case, I have to subtract this zero prefix, the null prefix, from this prefix, fine. But in the mask, we are not having any null prefix, fine. So this is something of an issue. So what we can do is initially, instead of the map or the dictionary being empty, we can store the prefix map, the null prefix map, and that we can simply say 000, because if there is no character in our substring, then every character is occurring zero number of times, that is 000. Fine. So this is one prefix that we should initially have in our map as well with a count of 1. Fine. So that to check if this substring from the start is good or not, we can XOR it with a null prefix. So this is how the algorithm goes, guys. And now let us move on to the implementation.
But before we begin, do you guys know that CodeChef also conducts free live sessions on Unacademy where we try to teach every possible topic related to competitive programming? We have list of courses for all skill levels like beginner courses such as Introduction to Programming in C++ and Java, intermediate courses like a course on number theory, recursion, basic data structures, as well as advanced courses like dynamic programming, graph theory, segment trees, and many more. Here, you will be taught by top coding experts who are IUI medalists, ICPC World finalists, and have worked at companies like Google, Flipkart, LinkedIn, and basically all those tech giants. All you have to do is register yourself at Unacademy by clicking this button Start Learning here and choosing your goal as competitive programming. But this isn't just it, guys. You can also go for the Plus subscription where you get additional benefits like individual support and full-time doubt solving. You also get the access to the problem sets curated by these coding experts for each topic. And to add the icing to the cake, there are mentors who are going to resolve all your queries, and they are 6-star and 7-star coders as well. So subscribe to Unacademy Plus, guys. Don't miss this golden opportunity of learning from the best in the world and kickstart your programming journey today. You can use the code Bharat27 to get an instant 10% discount as well. So hurry up, guys. Subscribe to Unacademy Plus.
So here's the code, guys. It will be in Python. So first, I have just defined two utility functions, ARR to string, that will take in a argument ARR and return the string corresponding to it. Fine. And another function, letter number, that is going to return 0 for A, 1 for B, 2 for C. Fine. And 26 for question mark, which is essentially 27 because of zero based indexing. Fine. Then to take the input for test cases as well as S. Then first, let us quickly just fetch the bit mask for S, that is the mask of S. Fine. And this I can simply find out by XORing all the corresponding values for the letter number of I. Fine. Then make a list all good that will contain the 27 possible good substring masks that we discussed in the explanation as well. So I am finding a list of all the possible good masks. Now here one thing, just as a side note, one thing to observe is that in bit masking questions we usually work with integers, but here to make it to make the implementation a little simpler, I have just used strings. Fine. So not integers but binary strings. Right. So then we are going to just define this the map that we saw in the discussion. The prefix is a dictionary initially containing the null prefix that is 0 27 times and its count is 1. Fine. Then the prefix mask, the PMI that we discussed, and answer equal to 0. Then for every I, we are going to first update our prefix mask, and then for each good mask, I'm going to find their XOR, the XOR of the prefix mask as well as the good mask. Then I'm going to increment answer by the value associated with the prefixes of XOR, or otherwise 0 if XOR does not exist in the prefixes dictionary. Fine. Then remember we need to add it to the dictionary as well, and the string of the ARR mask prefix. If it is already there, then we can increment its count. Otherwise, we can set it to be 1. Fine. So this is the code. Finally, we'll print out the answer. And now let's quickly submit the code as well. I've pasted it here. Let's hit the submit button and hope for anything. So yes, it is a correct solution, and this winds up the video.